Sorry that we had to restart the video. Hopefully this part 2 is coming nicely to you. Just to review what we've already been talking about, our big idea here is that work is going to be our change in energy, whereas energy is the ability to do work. Now we saw that in order to change the energy, in order to do work, we were requiring that a force as well as a distance requirement was met. So for our work, we saw that there was force times distance. And remember, the cosine theta was just there to kind of remind us that only the force that was being done parallel to the distance moved was actually counting. Now we're going to take a closer look at what our energy is. And we're going to see that when we have energy, our objects are going to be able to do work. So let's talk about energy. Energy can be in two major forms. We have what we call potential energy, and that's energy that's there. It has potential to do things. Nothing's really happening yet, but it has the potential. And we have the kinetic energy, and kinetic energy is going to be energy of motion. So when we take a closer look at these, there's many different types of potential energies, but in class we are going to talk about gravitational potential energy. Essentially, gravitational potential energy means that any object that has height has the ability to do work. Our equation is written right here for us, and it is showing us that we have our potential energy, G, gravitational, is going to equal the mass of the object, measured of course in kilograms, times the acceleration due to gravity, or as we know, 9.8 meters per second squared, times the height of the object, measured in meters. This is all equal to the potential energy, which is going to be measured in joules, which we abbreviate with just a capital J. And that what this is telling us is that anytime an object has height over another object, it has more energy. It has more ability to do work. Other types of potential energy are spring potential. When you squish a spring together, that has potential energy. The more squished it is, the more ability for that object to do work. We're not going to focus too much on that here, though. How does potential energy actually relate to work? Well, we're going to see it's essentially the same thing. Okay, we know that this part of the equation off to the right here, that's our potential energy. Okay, and that's just saying that is this man's mass times the acceleration due to gravity times his height. Then, on this side of the equation, we see the equation for work, force times distance. Well, in order to pull himself upwards, he has to overcome his weight. So his force would equal his mass times 9.8 meters per second squared. The distance that he gains is going to tell us how high he actually ends up being. So he applies this force for some distance from there all the way up to the top of the bar. It's going to go up like that, and we would know that that's his work. Well, if the distance is how much height he gains, we could plug that in right here for height, and we see that work is potential energy. When you do work to an object, you can be giving it potential energy. We've already talked about how work is the same thing as the change in energy. Before he started, he had less potential energy. Once he pulled himself up, he had more potential energy because he did work. You can see him moving up, and these are just going to go through. The force is what he's pulling up, and his distance that he's traveling is how much height he gains. Now, kinetic energy is slightly different. Kinetic is called the energy of motion, and it's going to equal 1/2 times mass times velocity. So we're going to see here kinetic energy which of course is going to be measured in joules, abbreviated by a J, is going to equal 1/2 times mass, of course in kilograms, times velocity, measured in meters per second, squared. Okay? Basically, anytime an object has any sort of speed, it is going to have energy of motion, or what we call kinetic energy. Objects can have a combination of many types of energies, and we'll take a look at that in our next few things. Now, in terms of work here, sorry, I'll just rewrite this over here. Work is the change in energy. So sometimes we'll see that work is going to be changing the amount of kinetic energy. If we go back to those wagon examples, we would be able to calculate how much work was being done by saying, okay, force times distance times our cosine of eta, and that would equal our 1/2 mass times our final velocity minus our initial velocity squared, because that's going to show us how much our kinetic energy changed during that time. In those situations, we are often bringing these objects to a stop. Woo! Energy of motion. So basically, we simply have to remember energy is conserved. This is kind of a big idea, and this is a major reason why we start talking about energy right after we've talked about momentum. Momentum was a conserved quantity. The total momentum of the system always remained the same. The same is true for energy. When I say conserved, I mean energy, total energy, is going to stay the same. The individual types of energy of an object can change, and that energy can be transferred from one object to another. But when we take a look at every single thing being affected, all energies add up to be the same at all points. We're not making energy, we're not destroying energy, we're simply changing it from one form to another. And what we mean by that is when we do work to an object, there's energy being used by one object to give a different object more or less energy. And that's kind of where we're going to focus our ideas. So, this is a huge thing. This total energy before equals total energy after. What we will be doing for all of these is we're going to focus on an object, and we're going to say, okay, its potential energy initial plus its kinetic energy initial has to equal its potential energy final plus its kinetic energy final. An object can have height, and it can have speed. If it has height, it has potential energy. If it has speed, it has kinetic energy. And so an object can have both of them at the same time. We are going to want to combine them to figure out our total energy before and set that equal to any other point, and that will equal its total energy at that point in time. Let's take a look at an example. Here we have an apple tree, okay, and the apple is falling. Let's say that the apple has a mass equaling 1 kilogram. And let's say this is a short little apple tree, okay? It's only 2 meters above the ground. 2 meters. At point 2, it's halfway down, so that's only 1 meter. Then at point 3, it's hitting the ground. Okay, let's go through and actually label what type of energy we have at each location. Here at the top, our apple has potential energy because it's just started its fall. It has a lot of height, but right when it's released, it's not going to have any speed, so there's no kinetic. At this point in time, at point 2, it has potential energy because it still has height, and it has kinetic energy because it's moving at this point in time. At the very bottom, it doesn't have any height, so there's no potential energy, but it's moving really fast right before it hits the ground, so it's going to have kinetic energy. So let's take a look, and in this situation, we want to figure out what is the velocity here at point 2, and what is the velocity here at point 3. So we can say that we know that the total energy to start has to equal the total energy at other points. So at point 1, all we have is potential energy. So the potential energy at point 1 has to equal the potential energy at point 2 plus the kinetic energy at point 2. So let's plug in what we know. Potential energy at 1 is simply going to be mass times gravity, or 9.8 times height at 1 equals my mass times gravity times height at 2 plus my 1/2 mass times the velocity at point 2 squared. So I'd plug in here 2 times 9.8 meters per second squared times, oops, sorry, this should have been simply 1 kilogram times 2 meters is going to equal 1 kilogram times 9.8 meters per second squared times height 2, which would just be 1 meter, plus 1/2 1 kilogram times V2 squared. So what I'm going to do here is I'm going to start calculating all of this. 1 times 9.8 times 2 is going to give me 19.6 joules. That's going to equal 9.8 joules plus 1/2 V squared. Now, I would like you to finish up this problem and see if you can calculate what V2 is going to equal. Then, for V3 here, let's do V3 solving this problem up here. I'm just going to set it up, and I, again, would like you to finish the problem. Try right now, see if you can get some of this set up, because this is the major idea here. Now, we could use at this time either whatever our potential energy at point 1 was, or our potential energy plus kinetic energy at point 2 was. Since it's easiest just to think about one number, I'm going to say that my potential energy at point 1 is going to equal my kinetic energy at point 3. Now remember, at point 3, there's no kinetic energy, or there's no potential energy because it doesn't have any height. So this is simply going to be mass times gravity times height at point 1 equaling 1/2 times mass times velocity at 3 squared. So this would just be my 1 kilogram times 9.8 meters per second squared times 2 meters equaling 1/2 times 1 kilogram times V3 squared. See if you can solve for that velocity. We'll talk about these answers in class tomorrow and go over some of these major concepts. Hopefully what you've learned from today is that work is going to be a change in energy, and energy is the ability to do work. Also, very importantly, we see that energy is conserved at every point, and we can identify what types of energies we have, whether they be potential or kinetic or a combination of the two. All right, I will see you guys in class tomorrow. Have a wonderful evening.